and look at the symmetry of functions. This is not going to take very long at all, maybe about 20 minutes. For some reason, I have a feeling that my battery might be running a little low on one of my microphones, so please, somebody let me know if my voice dies. This is under the heading of Symmetry of Functions in Lesson 5.0, so this is just a continuation of where we left off. We're going to talk about two types of symmetry. And basically, a function will either have symmetry or it won't. And if it does have symmetry, the function will be either even in terms of what we call the symmetry, or it will be odd. Now, a function is considered even if the graph of the function appears symmetrical with respect to the vertical axis. And what that's going to mean, we'll explain this next part in more detail, but what it means is that f of negative x is the exact same thing as f of x. So here is an example of a graph that is considered even. And we can see that it's symmetrical with respect to the y-axis. What that means is that if you were to take a look at the part of the graph that's to the left of the y-axis and take that graph with an invariant point right here, take that graph and reflect it across the x-axis, then you would get the other half of the function. So that's what it means to say a function is even. That's what it looks like. Now, what's the whole deal with this f of negative x equals f of x thing? Well, we're going to start off by talking more specifically, not generally, but more specifically, about a particular x coordinate on the graph. So I'm calling that x coordinate a. Now, that x coordinate might be 5. But if I asked you to determine the y coordinate at that x coordinate, you would simply read off of the graph what the y coordinate is. And that y coordinate is what we call f of a. And I didn't include that on this diagram because it will get too cluttered, but I will write this in just the first time and say to you that what that number is f of a. It's the y coordinate at x equals a on the graph. Well, now if you look at an x coordinate of negative a, well, what does this mean? It means that whatever number a was, the new x coordinate we're talking about is the opposite of it. So if a was at 5, negative a is negative 5. And what we discover, and it's only because it's symmetrical, is that you get the same y coordinate. If I ask you what the y coordinate at negative a is, you get the same number as the y coordinate at positive a. But the y coordinate is f of a and f of negative a, which means f of negative a and f of a are equal to each other. We can take any other value of x. 0, it doesn't really work because we run into problems where there's not a negative of 0. The negative of 0 is still 0. But if we go over further and look at b equals some other number like, I don't know, 10, that y coordinate on the graph at that point is f of 10, or in a more general sense, f of b. If I go over to the other side and I look the same distance away from the axis on the other side at negative b, so if b was 10, now I'm at negative 10, we discover, and again it has to do with the symmetry of this picture, that the y coordinate for both of these points is the same, which means f of negative b and f of b are equal. Well, I mean, I could go on and I could pick a million other points and demonstrate that to you, but what we say in general then for the graph is that f of negative x gives you the same thing as f of positive x. And that's the definition of a function that's even. Let's take a look now at a function that's odd. What does it mean to say a function is odd? That doesn't mean it's peculiar or strange. It means that it's symmetrical with respect to the origin. So I don't want to get into the function notation just yet, but this is a function which is odd. And it is odd in terms of its symmetry because if I take everything to the left of the y-axis. If I reflect it across the y-axis, I will not get the part that's to the right of it. But there's two ways to demonstrate how to get the part to the right. If I take that part that's to the left and I reflect it horizontally, and I'm just going to change the color of that, and I reflect it horizontally, it ends up being here. But then if I reflect that vertically, it ends up being on the other part. So one of the ways to explain how to get the left-hand part to turn into the right-hand part is to say that we have to reflect it horizontally and we have to reflect it vertically. There's another way to explain it, and it doesn't work very well on the smartboard. It's to take this part and pivot it, but pivot it around the point that's on the origin. And I didn't set it up so it will work. But if I could somehow lock that origin in place and pivot it, by the time I pivot it all the way around with that origin there, I end up with that position. So one of the things you might notice is that an odd function must go through the origin if it's defined at x equals 0. If you have a function that's defined at x equals 0 and it's odd, it has to go through the origin. This is not odd. It's got to go through the origin. You can tell it's not odd because the part on the right has a piece that's above the y-axis or the x-axis, and the corresponding kind of sister region to it is still above. It's got to be opposite in every way. Now let's talk about the function notation. So if I were to take a point, an x-coordinate called A, and I look at the y-coordinate at that point, the y-coordinate has some value, and that value again is f of A. If I look now at the negative of A, which is, I want to make sure you get this because it's important for the visual, this distance here and this distance here are equal. Because if A is 5, negative A is negative 5. And if you take a look at the y-coordinate when x is negative A, you get a number which is not the same as the y-coordinate when x is A. But because it's symmetrical and this distance are equal, this distance and this distance must be equal. Which means that f of A, which is the y-coordinate here, and f of negative A, which is the y-coordinate here, have the same value except one's positive and one's negative. In this case, f of negative A is a positive number, and f of positive A is a negative number. But what is important is they are negatives of each other. So what this means is that f of A, which is the y-coordinate at negative A, is equal to negative 1 times, I'm going to say that again, f of negative A, which is the y-coordinate at negative A, is negative 1 times f of A, which is the y-coordinate at A. This is just a very fancy way of saying they have opposite values for the y-coordinates because their x-coordinates are opposite. Take another number, b. The vertical location of that line is f of b. If I look at negative b for x, and I look at the vertical location of that point, that's f of negative b. Again, they're negatives of each other. If f of b, if this number here is 3, then f of negative b is negative 3. All this statement is saying is the two y-coordinates are opposite. So if we make that more general, that means that f of negative x is going to give you the negative of whatever f of x is. And then we have neither. I mean, a function doesn't have to have symmetry. If you take a look at this graph, and by the way, this is the graph we were just looking at, but I've changed its location relative to the axes. If I were to take a look at an x coordinate of a and track the corresponding y coordinate, that's f of a. And if I look at negative a, which is, again, everybody, this distance is the same as this distance. I'm just as far to the left of the y-axis to get to negative a as I am to the right of the y-axis to get positive a. But anyway, if you take a look at f of negative a, we have that. So now, is f of negative a equal to f of a? Well, no. And I have a typing mistake here. I see it right now. I'll just cover up this. They are not equal. F of negative a is not equal to f of a. If I take a look at these two y coordinates, are these two y coordinates negatives of each other? Well, no. So that means that f of negative a is not equal to negative f of a. And what that means, I could have put a's in there, but what that means is that this function is neither odd nor even. Take a look at another one. This is this wacky graph. Pick an a coordinate. That represents f of a. Pick the negative of that. Again, I hope you get this, but I would rather be overly repetitive to make sure you get it. Those two distances are equal. That represents the location vertically of f of negative a, which means that f of negative a is not the same as f of a, and f of negative a is not the same as negative f of a, which means that f of negative x is not equal to f of x, so it's not even. F of negative x is not the same as negative f of x, which means it's not odd, and that means it's neither. So that's the deal behind symmetry. Does anybody have any questions about those three types of descriptions for graphs? All right. So, one question, 3 parts. Classify each function as odd, even, or neither without graphing it. So we want to know if this is odd or even or neither. So what we could do is this, and I don't want you to do this. You could if you wanted to, but you don't need to. We could pick an arbitrary number for x. I mean, I could pick I could use x equals 4. And I could calculate f of 4, and then I could calculate f of negative 4. And I could see what happens here. I could find f of negative 3, and I could find f of 3, and see what happens. I'm going to actually do that. We're not necessarily writing this down because it's not the proper way to answer the question. But if I put 4 in for x there, I'm going to get 2 times 4 raised to the 5 minus 3 times 4. I'll just double check my substitution. F of 4 would be 2 times 4 to the 5 minus 3 times 4. We end up getting 2036. While I'm at my calculator, I'm going to do the same for negative 3. I'm going to put negative 3 in there. 2 times in brackets negative 3 to the 5 minus 3 times, we don't really need in brackets, but I'm going to put it in brackets. 2 times negative 3 to the 5 minus 3 times negative 3 gives me negative 477. So if you were to calculate f of 4, you would get 2036. And if you were to calculate f of negative 3, you would get negative 477. Now, trust me on this because I know that this function is odd by looking at it. If you put negative 4 in, then you will discover that you get negative 2036. And if you put positive 3 in, you will discover that you get positive 477. So f of 4 is the negative of f of negative 4. F of negative 3 is the negative of f of positive 3. So this function is odd. But doing this that I have written is not proving to me that the function is odd everywhere. I hope you would agree it would be pretty strange if we did this for hours upon hours, and then all of a sudden we found one particular number where it didn't work. But that's the nature of math. You don't prove something is true by showing it to be true in a couple of cases. So how are we going to actually do this? Well, we're going to find f of negative x. What is f of negative x? I'll remind you of something, that if I gave you that function and I said, what is f of pi? It would be 2 times pi to the 5 minus 3 times pi. If I said, what is f of puppy? It's 2 times puppy to the 5 minus 3 times puppy. And as I've said before in class, don't be put off by the fact that we're using puppy. Any variable or number or item in mathematics is just a bunch of scribbles on paper anyway. And the point I want to make here is that f of a thing is the result of putting that thing in for x. So f of negative x is 2 times negative x raised to the 5 minus 3 times negative x. And we're finding f of negative x so we can compare it to f of x. Because if we get the exact same thing, then the function is even. If we get the exact opposite thing, it's odd. And if we get something that's neither, then it's neither. So I'm going to simplify this using my knowledge that a negative base raised to an odd exponent means you're going to be multiplying the negative base by itself an odd number of times, which is going to create a negative result. So in brackets, negative x n brackets raised to the 5 is the same as negative x to the 5. And we've got a coefficient of 2. Of course, we know negative 3 times negative x is positive 3x. And now what we want to do is compare that. We're doing a comparison here to f of x. Well, f of x was 2x to the 5 minus 3x. And we can see that if you were to multiply f of x by negative 1, you would get f of negative x. Or, if I take f of negative x, and be careful, look at the notation here. This is f of negative x, this is f of positive x. I'm going to write f of negative x again down here. I can take a negative 1 out of this and be left with 2x to the 5 minus 3x. But this, without the negative 1, is f of x. Which means f of negative x gives us negative 1 times f of x, and that's the textbook definition of an odd function. We've covered every single x and y coordinate pair. Does that first example make sense? A bad question for me to ask. Does anybody have any questions with that first example? All right. By the way, I knew that this function was odd because the degree on each term is odd. Now, it gets trickier than that, so be really careful here about drawing a conclusion that you might not be able to draw. Basically, if I have a polynomial function and one of the terms contains the variable to an odd exponent, anytime I put negative x in there, it's going to change the sign on the term. So if all of the terms are odd, in this type of example, the function is odd. Now, let's take a look at this next one. We could certainly come to the conclusion it would be wrong. Mr. Wade just told us, well, if all of the exponents are odd, then the function is odd. That's not going to happen here. Again, we don't want to put numbers in for x. Let's put in negative x for x. So I'm going to have in the numerator negative x cubed. And the fact that I have it in brackets and then the cubed outside of the brackets is absolutely crucial to what's going on here. Over 2 times negative x in brackets, quantity to the 5, minus 3 times negative x as a quantity. So we simplify all this. F of negative x, the numerator becomes negative 1 x cubed. We certainly don't have to write negative 1 x cubed. We could just write negative x cubed. Over, the denominator becomes negative 2x to the 5 plus 3x. And then we want to compare that to the original function. And if I were to take that expression for f of negative x and factor a negative 1 out of the bottom, out of the denominator, then I would be able to cancel the negative 1's, because negative 1 is a factor of the numerator. It's in brackets being multiplied. And negative 1 is a factor of the denominator. Those negative 1's cancel, which means f of negative x is x cubed over 2x to the 5 minus 3x. But this whole thing is f of x. Look at the original function. F of x is x cubed over 2x to the 5 minus 3x. So what have we concluded? We've concluded that f of negative x is equal to this thing on the right, which is f of x, which means for this function, if you put in a value for x and then the negative of that value for x, you get the same y coordinate, and that means it will be symmetrical across the y-axis, and that means it will be even. Now, with experience, you don't necessarily have to do this. I could have told you that this was even, because if the top of this expression is odd, and it is because the exponents in the top are all odd, and the bottom of the expression is odd, because all of those exponents are odd, then the top will be the negative of the old top, the bottom will be the negative of the old bottom, and the negative of and the negative of cancel. By the way, for the purposes of odd and even, well, we'll just go to the next example. The degree on the x in this 3 in the denominator is 0. 0 is even. 0 is an even number. So I know by looking at this whether it's odd or even, but let's go through the procedure. We put in negative x for x. We'll get negative x quantity squared. I hope you see that because this top exponent is even, when I put in negative x, it's not going to have any effect on the top because I'm going to be squaring a negative. And that would be true if it were a power of 4 or a power of 6, any even exponent. On the bottom, we have 2 times negative x quantity to the 3 minus 3. I don't think it's necessary for us to put negative x to the 0. The bottom becomes negative 2x cubed minus 3. So the first question you ask is f of negative x the same as f of x? Is this thing identical mathematically to this thing? And the answer is no. It's not, because the coefficient of one of the terms on the bottom is 2. The coefficient on the bottom in the new thing is negative 2. These are not equal. Then you ask, well, is f of negative x equal to the negative of f of x. And what that means is if you were to multiply this by -1, would you get that? And the answer is no. If this, looking at the bottom of your screen here, there we go. Looking at the bottom of your screen, if you ended up with, and it would be impossible to do so in this example, if you ended up with +3, then the function would be odd, because if I multiply something by -1, that means I can multiply the bottom by -1. And if the 2 changes to a -2 and the -3 changes to a +3, that's odd. But let's, wake up and come back to reality here, because it is not +3. It's -3. What does this mean? It means that f of -x is not the same as -f of x, so it's not odd. And if it's not even and it's not odd, then it's neither. In other words, this has no symmetry. I want to take first two things. Any questions with that? I want to take a moment here and talk about the example we did here where we sketched this graph. When you take a look at this function, 3x to the 5 minus 25x cubed plus 60x to the 1, that's an odd function. If you put -x in, what you're going to get is -3x to the 5 plus 25x cubed minus 60x. Because all of the exponents or powers or degrees are odd, then that's going to flip the signs on everything. And this is why when we look at the critical numbers, you have critical numbers which mirror each other. If there's a critical number at -2 and the function has some kind of symmetry, whether it's odd or even, then we'll also have a critical number at 2. By the way, since this is odd, I mean, I did all of the work here, but if this is odd, we created a table. Let me show you the table. Remember we found the y coordinates? I don't know if you remember, but I didn't worry too much about 2 of these, because I knew that if at -2 you had a y coordinate of 16, -16, I knew at +2 it had to be +16 because it's odd. And take a look at that graph. That is odd. If I take, I mean, I didn't draw it perfectly, so it might not work out well, but if I take this thing and I rotate it 180 degrees, that's not bad. Actually, that's pretty good. It's not perfect, but you get the idea. So when I said to you earlier, you're going to have to do a lot of stuff, knowing symmetry will allow you to cut some corners, will allow you to take some shortcuts. So that's it for symmetry. As I said to you before, these two problems, which you've been working on for about the past 20 minutes to a half an hour, this deals with intercepts and first derivative chart, or first derivative analysis, whatever you want to call it. These questions deal with symmetry.